Good afternoon, everyone, and welcome to the second online energy plan workshop. I hope everybody can hear me. I'll just put a notice up. So hopefully nobody has any technical problems. And the workshop today is going to last approximately 1 hour, and the agenda for today is heat pumps. And hopefully, if we have time, I'll get to do an analysis of both large-scale and individual heat pumps. And along the way, I'm going to do this as a live demonstration of how I would do any analysis, just to bring you through the steps that we always take when we do some sort of scenarios in EnergyPLAN. So the agenda for today is divided into two. The first part of the workshop is going to focus on large-scale heat pumps, and the second part of the workshop is going to focus on individual heat pumps. And I'm going to end the workshop with a first preview of the new energy plan, which will be launched in January, hopefully. But we just finished some major new developments on the interface, and I'm going to give you a sneak peek of what's going on behind the scenes by the development team. I think if anybody would like to, I imagine you can follow along as I do this demonstration today, because I'm going to start at the very beginning and work my way through. So if you have a copy of EnergyPLAN on your computer, then I think you should be capable of following along the steps yourself if you want to replicate what I do. But if you don't have the time to focus on both things at once, the recording will be distributed afterwards, so you are free to copy what I do along with the recording after the presentation. I've also put a list of some key steps that we'll carry out during the demonstration in the agenda here. So I'm simply going to follow these steps. You can see 1, 2, and 3, so that you have a template to take away with you afterwards in terms of how I did the demonstration. Otherwise, I think we're good to start. So welcome to virtual Copenhagen, and I hope you get something useful from the workshop. I'll begin by just opening EnergyPLAN, hopefully the same copy that you have. It's the latest public version of EnergyPLAN, which was released earlier in the summer. So it's version 11.4, and it was released in May. And when we start any analysis in EnergyPLAN, the first thing that we always recommend you do is open what we call the Initialize file. So hopefully everybody can see my mouse, and I just clicked on the open button on the top left corner, and when I do that, I'm brought to a default folder list for EnergyPLAN where you can see a file called Initialize. And when I open that, all of the inputs in EnergyPLAN are now put to 0. So I have a fresh, brand new canvas, you could say. So that's always a good idea to start with, just zeroing all of the inputs in EnergyPLAN. The next thing I will do then is I'll save that as a new file. So file, save as, and I'll call it workshop2.txt. So EnergyPLAN saves files as text files. So just always make sure you have the file name .txt at the end. So now I've called this workshop 2, and I have a brand new blank model. The next thing I'm going to do at the very beginning is I'm going to load all the cost data into EnergyPLAN. And the reason I do that at the beginning is because we actually provide a cost database for people who use the EnergyPLAN model to save you months of hard work collecting lots of statistics about different technology, data, costs, and so on. So if I go to the cost window, and then under the additional tab sheet, at the very, very bottom of this window, you can see that there's some options here to save and load cost data. And this allows the user to load data just for the cost tab sheet. So for those who are familiar with EnergyPLAN, you'll recall that we have 5 key tab sheets at the top, and by using these load and save features under the additional window, I'm only affecting the data under this main cost tab sheet. And if you want a copy then of the standard cost data that we provide with EnergyPLAN, you can get that from our website. So I'll just demonstrate right now. If I go to www.energyplan.eu, then from the models drop down, you'll see something called cost database. And I just updated it today because I noticed there was a lot of numbers we had changed since we last updated it 2 years ago when I was preparing for this workshop. So now you'll see that version 2 of the cost database is available as a zip folder. And if you select that, it should download as a zip file. So you can see on the bottom left of my screen that the file is downloading. And then if I go to my downloads section, you can see that I have cost database version 2. So I'll unzip that. And when I unzip it, I should get a text file and a PDF file in this folder called Cost Database 2.0. So in here you can see that there's a PDF file with some details with documentation of where the costs come from, and then there's this cost file which I can use to import costs into the EnergyPLAN model. To import those costs, I have to open the EnergyPLAN folder where the model is stored. And for those of you who have already downloaded EnergyPLAN, you'll recall that there's these 3 main folders: EnergyPLAN Data, EnergyPLAN Help, and EnergyPLAN Tools that come when you download the EnergyPLAN model. And if I go into the EnergyPLAN Data folder, there's a folder called Cost, and then I must store these cost files in here. So if I copy this file I just downloaded into that folder, I can now load it into the EnergyPLAN tool. So let's try that out. Load new cost data. Then I'll select the one with today's date and click open. And when I do that, you can see that now all of the costs have values associated with them. So the investment sheet, the operation sheet, and the fuel sheet have all been populated with statistics that we have gathered over many years to fit with the EnergyPLAN inputs. And the reason, as I mentioned before, that I do this at the very beginning is because I don't want to do this after I have put information in the rest of the EnergyPLAN model in case there's any errors with the loading function. So I always do this at the beginning of an analysis. Create a new folder, a new file with the initialize.txt file so that it's blank, and then load in the cost information that you plan to use in your analysis. You'll see that my main folder, my main file is still called workshop2.txt, so I'll just save that file, save as, and workshop2.txt again, just to make sure that I've everything saved now and ready to go with a fresh new study. So that covers, going back to our agenda, the first 2 key parts of starting an analysis: loading the Initialize file and then importing your costs. Now I need to build a reference model so I can carry out some analysis today. And I just made up a reference scenario which is a typical country of Danish size, I would say, maybe a bit smaller. So it's just an imaginary country with some electricity and district heating demands that I created to be able to perform the large-scale heat pump analysis today. So I'm just going to follow these instructions that I made earlier today about what exactly it should look like. So the first thing is, in my imaginary reference scenario, we have an electricity demand of 20 terawatt hours and a district heating demand of 10 terawatt hours. So if I go back to my model, I go to the input tab sheet, and under the input tab sheet I always insert technical characteristics of the energy system. So the input tab sheet is where I put things like efficiencies, capacities, annual productions and consumptions, anything that's technically related to the energy system. So I have a 20 terawatt hour electricity demand. So here under input electricity demand, I'll insert 20 terawatt hours. So you can see now my total electricity demand is 20. Secondly, I have a district heating demand of 10 terawatt hours. So if I go to the district heating tab sheet, I want to here insert the type of district heating demand that I have. One of the questions that I got before the workshop was to try and describe why there's 3 different types of district heating. So I'll try and do that now, but hopefully I'll make it clearer rather than make it more confusing, because it might be a bit difficult over the conference call system. But let's try. I'll just explain that EnergyPLAN is divided into these 3 different groups in terms of district heating. Group 1, Group 2, and Group 3. And this is described in detail in the FIDE guide. So if I go to the EnergyPLAN website and I go to training, we have something called FIDE guide, which is finding and inputting data into EnergyPLAN. So afterwards, if you're still finding this confusing, there's a detailed explanation in this report about why these 3 groups exist. But just very briefly to describe them, they are distinguished between 3 groups to try and distinguish between the different characteristics of CHP plants that are on the district heating systems. So let's start with Group 3. That's typically the easiest one for people to familiarize themselves with. Group 3 district heating is for district heating systems that are located in large cities typically, where the power plant, that's CHP plant, is located near a river or the sea. And the reason that that's important is because if a power plant is located near the river or the sea, it means that it can produce electricity on its own and waste the heat into the heat source, which is the river or the sea. In other words, the CHP plants on these district heating Group 3 components are able to produce electricity independently of supplying heat to the district heating system. And that's very important because, for example, in the summertime, when people have a very low heat demand, there might be times where you would like to operate your CHP plant without providing heat to the district heating system because people don't need it. So this is the type of CHP that's on the district heating Group 3 systems in EnergyPLAN. Group 2 then is slightly different. In district heating Group 2, we have CHP plants that have no heat source to be able to dump the heat if they don't want to provide it to a district heating system. So a district heating Group 2 demand is for systems where the CHP units must produce heat when they produce electricity. So whenever you have to produce a unit of electricity, you also have to produce some heat for the district heating system. And this is very important because it means that these CHP plants don't have the option of producing just electricity on its own. So whenever they want to produce electricity, there also has to be a heat demand on the district heating systems. And this connection between electricity and heat makes these CHP plants a bit more difficult to accommodate than the CHP plants that are in Group 3, for example. So I hope that's clear now that Group 2 is for CHP plants that have a connection from electricity and heat together, whereas Group 3 is for CHP plants that can produce electricity independently of heat. Finally then, Group 1 is for district heating systems that have no CHP plants. So these are usually very small district heating systems that only have, for example, a boiler providing heat to them. So in today's demonstration, I'm just going to assume that the 10 terawatt hours of district heating demand that we have is all on group 3 type systems. So I'm simply going to put in my demand here of 10 terawatt hours of district heating. And you could say that I have now constructed the demand side of my reference system that I'll use today. I have a 20 terawatt hour electricity demand, and I have a 10 terawatt hour district heating demand. So let's go back then to our agenda, and step 3 is now complete. So we'll move on to step 4. And here we're going to create the supply side of our system that we're going to use as the reference. And what I've got is firstly some power plants and some CHP plants to provide both the electricity and the heating. And I wrote here that I have a total of 4,000 megawatts of gas power plants, and 1,000 megawatts of these are CHP plants. So 3,000 megawatts produce electricity only, and 1,000 megawatts are combined heat and power plants. So if I go to EnergyPLAN, it says in here PP condensing. That's where I input my total power plant capacity, which is 4,000 megawatts. Over on the right hand side, I have the distribution of fuel, where I specify what type of fuel these power plants burn. So for example, PP, which is what I've got, 4,000 megawatts, I want to specify that that's all gas. So I put in a 1 here, for example, under natural gas, and that means that 100% of the fuel that those power plants consume is natural gas. If I was to put a 1 under coal, then the model would be instructed that 50% is coming from coal and 50% is coming from natural gas. So the model uses the ratio between these 4 fuels to define what type of fuel goes into the power plants. I'm going to just repeat that last sentence again. If I put 1 here under coal, then it would assume that I have 50% coming from coal and 50% coming from natural gas. But I want to assume that all of it is coming from natural gas, so I put in a 0, because the model uses the ratio between all of these fuels across here. So that means that I have now installed in EnergyPLAN 4,000 megawatts of natural gas power plants. But in my reference scenario, I wanted to specify that 1,000 megawatts of this 4,000 is capable of operating in combined heat and power mode. So I put in 1,000 megawatts here under the CHP3 capacity. And then over here, I once again want to specify that all of those CHP plants are natural gas. So I put a 1 under natural gas to signify that they're 100% natural gas. Now this is where the benefits of using a tool like EnergyPLAN start to become evident, because if I go to my cost window now, you can see that these costs are automatically updating all the time as I put in new inputs. So I have 1,000 megawatts of CHP units, and I have 3,000 megawatts of power plants. And using the cost database inputs that we provided, these are the total costs for each of those components that we're now constructing on the system. So it saves you quite a lot of time from making these calculations in an Excel sheet, for example. If we, on a district heating system, not only do you have CHP plants, but you very often have boilers and thermal storage facilities also to facilitate how these CHP plants operate. And in my agenda, I put in some golden rules that we typically use if we're designing a system that we don't have statistics for. So for example, I want to put in some gas boilers on the same district heating systems that I have the CHP plants, and we usually put in a total boiler capacity which is equal to 120% of the peak heat demand over the year. Thermal storage, a good guideline is 5 hours of average heat demand for the thermal storage capacity. So I'll just repeat those again. With the boilers, it's 120% of the peak heat demand, and for the thermal storage facilities, it's 5 hours of average heat demand, or typical sizes that are required on the district heating systems. So then I want to show you where we get those type of values from. And the first thing that's very important now is this distribution of demand. So this distribution here specifies for each hour of the year how your heat demand is distributed. And these distributions are stored in the EnergyPLAN folder called distributions. So if I go back to the parent folder of EnergyPLAN again, once again, for those of you who have EnergyPLAN installed, you'll remember these 3 folders that come with the model. If I go to EnergyPLAN data, and then under that I'll find that there's a distributions folder. And in here is a library of different distributions that people have created over time. So if you have a distribution for your specific scenario, you can create a text file with 8,784 inputs, one for each hour of the year, and you can store it in this folder and then load it into the EnergyPLAN model to explain to the model how your annual heat demands are distributed for each hour of the year. For my made-up world, I'm just going to stick with the standard distribution that comes when you start an EnergyPLAN model. So I'm going to leave it at this hour distribution heat.txt that's already used. So this hourly distribution is explaining to EnergyPLAN how this 10 terawatt hours is distributed for each hour of the year over a 1-year period. So what I want to do then is I want to run the EnergyPLAN model and find out what was the peak heat demand when I use this hourly distribution and this total district heating demand over the year. So I'll press the run button. I'm going to run this to the screen, which is this run button on the left, and the results will pop up on a screen in front of me. If I then scroll down, I'll see that there's a lot of data here for lots of different components within the energy system. And one of them is called district heating. And you can see that I have a total demand over the year of 10 terawatt hours, which is what I expected. And then at the bottom, you can see that it gives you what is the average heat demand over the year, what is the maximum heat demand over the year, and what is the minimum heat demand over the year. And here we can see that the maximum heat demand on the district heating system was approximately 2,000 megawatts of heat. So in the golden rule that I mentioned earlier, I said that we usually estimate the boiler capacity as 120% of this maximum heat demand of the year. So if I just open my calculator and I take this 2025 by 120%, I find out that the boiler capacity I should have is approximately 2,430 megawatts. So based on that, I'm going to install a boiler capacity of approximately 2,500 megawatts. Then if we look at the thermal storage, I mentioned that it should be 5 hours of the average heat demand, and in this case the average heat demand is 1,138 megawatts. So 1,138 megawatts by 5 hours is about 5,700 megawatt hours, and that's approximately 6 gigawatt hours. So this gives me an indication of what my thermal storage capacity should be. So if you ever are carrying out some scenarios for the future and you want to design some new district heating systems, then these are good rules of thumb or indicators of what range of boilers and thermal storage capacities you can start your analysis with. Of course, you can then analyze these different capacities to see which makes the most economic sense and so on, but at least you have a starting point when you use these thumb rules. So let's go back to the model now, and I'll install on the input district heating tab sheet the boiler capacity of 2,500 megawatts, and then I'll go to my fuel distribution and specify that that's all natural gas also. Then I'll go back to my thermal storage capacity and specify that that's 6 gigawatt hours of thermal storage in the system. This means that I have now completed a very simple reference scenario. I have a 20 terawatt hour electricity demand with the standard distribution that comes with EnergyPLAN, which you can change if you have some data for your own country. I have a 10 terawatt hour district heating demand, which is being supplied by 1,000 megawatts of CHP, backup boilers of 2,500 megawatts, and a thermal storage capacity of 6 gigawatt hours. Then for any electricity that's not provided by the CHP, I have 3,000 extra megawatts of electricity only plants. And all of these plants are going to consume natural gas. When I run this type of scenario, then the natural gas that is consumed by the power plants will be paid for based on the price we've assumed in the cost window. So if I go to the cost window and fuel, you can see that when I loaded in the costs, I assumed that there was a price of 9 euros per gigajoule for the natural gas that I buy. I should just highlight that I can see a mistake now in the model because the cost database that I loaded was in euros, but my file or my model in EnergyPLAN was using kroner. I need to change these settings from Danish kroner to euro. So I can do that under the settings window and then clicking change unit for the monetary unit. And you can see that I changed to euro. So if I go back to the cost window, now it's in euros per gigajoule. And it doesn't have any effect on the numbers themselves. It's simply for reporting purposes that you need to make sure your currency is aligned with your input data. So let's run the model now, and what I would usually do with this reference scenario when I begin is first of all I'll just run the model and see what type of results. So if I run it on the screen so you can see it also, you'll see that the total costs of my reference scenario are approximately 3.5 billion euro each year. And that's the price of paying for the operation and maintenance costs and paying for the fuel that I consume in the power plants. Some other interesting things that people like to measure are CO2 emissions. So you can see that this reference scenario is producing approximately 10 million tons of CO2, and the total fuel consumption is approximately 48 terawatt hours. So these are some interesting things that people measure when they do these type of analysis. The last thing then I'll just do is I'll specify my type of optimization in the EnergyPLAN model, and I'll change it from technical optimization 1 to technical optimization 2. And basically what that means is that I'm telling EnergyPLAN to try and adjust the output of the CHP plants to accommodate wind power. And there's a lot of other details about that, but I won't get into them on this tutorial. I'll just use this for the study that I'm about to carry out. Then the really interesting thing that EnergyPLAN can do that's extremely useful for your analysis is we can start adding some wind power to this reference system to see how the costs and the performance of the system will change as we add more and more wind energy. And we can do that under the Output tab sheet, where we have something called Run Serial Calculations. So this serial calculations option allows you to change an input in EnergyPLAN and run the model for each one of those inputs and give you some results. Hopefully that'll become clear after I demonstrate it. So the first thing I need to do is turn the serial calculator on. Then I need to specify which input I'd like to change. So you can see that if I press this button repeatedly, the input will vary between all the different types of renewable energy. So I'm going to vary wind power, and then I can specify what values I would like the serial calculator to use when it does its calculations. So usually when I do this, I'll go back to my renewable energy tab sheet, so input renewable energy, and here you'll see all the different types of renewable energy. And if I type in, for example, 1000 megawatts of wind, you can see that I'm producing 2 terawatt hours of electricity. And that's actually quite low. Let's just check the capacity factor of that. So I have 2.07 terawatt hours, and that's from 1000 megawatts. If that 1000 megawatts operated for all hours of the year, let's just calculate that. So I'm multiplying 1000 by the number of hours, then I would get approximately 8.7 terawatt hours. So what I've done here is just calculated what the production would be if the wind operated all the time. So if I had 1000 megawatts operating all hours of the year, I would get 8.78 terawatt hours. And if I divide this 2.07 by this 8.784, then I'll get 23%. 23.6%. And that's the capacity factor of that wind turbine. And I would say that that's relatively low. Typically a wind turbine would have a capacity factor of 30 to 33% or something like that. So I'm going to change this 2.07 terawatt hour production in EnergyPLAN so it has more operating hours than what its distribution that's in use right now has. And we can do that in 2 ways. We can do it by changing this hourly wind distribution to a new one, so the hourwind1.txt file to another wind distribution. So I'll just search and I can see here, for example, Danish wind. And if I try that, you can see that that's gone down even more, which is also unusual. So I'll go back to the original one. Our wind 1, I believe. And instead of changing the distribution, I'll just increase the amount of full load hours on the wind distribution curve using this correction factor, so that my capacity factor is higher than what this distribution is saying. So I think a capacity factor of approximately 30% would be more reasonable for a wind turbine. At least in a Danish case, 30% would be very reasonable. So let's say we try 2.5, that's 28, so 2.6 terawatt hours, 2.7, yeah, so we'll say 2.65 gives you a capacity factor of approximately 30%. So I'm going to increase the production from the wind turbines so that I get a capacity factor of around 30%. which would be more reasonable. So I'll change this correction factor so that the production is now 2.68 terawatt hours instead of the original 2.07 terawatt hours. And this correction factor does that by increasing the amount of hours where you have extra production from this distribution curve. And there's an explanation in the documentation that comes with EnergyPLAN of how exactly that calculation is made under the help documentation list. And I just want to do this because the capacity factor of our wind turbines is going to have a big impact on the benefits from our large-scale heat pumps that we analyze later on in this demonstration. So I just want to make sure that the capacity factor is at a reasonable level. So now we have 1,000 megawatts of wind produces around 2.7 terawatt hours. So approximately 7,000 megawatts produces almost 20 terawatt hours, which is the electricity demand that I have. So I'm going to vary the wind power in this system from 0 to, let's say, 7,500 megawatts and see what the impact is for different amounts of wind power. So I do that by going to my output sheet, and then I'm going to vary this wind by 0, 1,000, 2,000, 3,000, 4, 5, 6, 7, and so on. And I'll end with 7,500. And then I don't need the last two inputs on the serial calculator, so I'll just get rid of those. So now I'm telling the serial calculator to run the model for all of these different amounts of wind power. And the last thing I need to tell the model is what to measure for each of these different wind capacities. And I tell it what to measure by clicking this button where you can see the output is varying every time I click it. And for this analysis, let's measure the total costs. So what we'll investigate now is, will wind power reduce the total costs of the energy system as the capacity of wind power increases from 0 to 100% of the electricity demand? And I know that 7,500 megawatts represents 20 terawatt hours because I just tested it on the input renewable energy tab sheet. The next thing I'll do is just set up a sheet in Excel to record my results. So I'll call this wind capacity megawatts 0, 1,000 all the way down to 7,000 and then finally 7,500. And I'm going to measure the total costs in million euro per year. So if I run my model now, I press the clipboard button and you can see that EnergyPLAN starts calculating the total costs of the system for each of those wind power capacities. The price of the wind turbines is linked to the price under the cost investment tab sheet that I input. So you can see here wind has these prices from the cost database. So this is the cost of building the wind turbines in our model. And if I paste those results, so right click, paste, you can see that this is how the total costs of the system varied for each amount of wind capacity installed. And I can see here that this is the cheapest wind turbine capacity on this system. So if I install 4,000 megawatts of wind power, then I will reduce the cost of my reference model from 3.5 billion euro per year to 3.2 billion euro per year, or something like that. After that, the price starts to increase again because I'm losing too much of the wind power. So that's, you could say, how good our reference model is at integrating wind. So now we're going to try and measure something else. Maybe another thing I will measure is surplus electricity, to see how much of the electricity from the wind production am I losing each year. So if I go back to the EnergyPLAN model, output sheet, and I'll change this output from costs to something called critical excess electricity production, or CEEP. So CEEP, which is the surplus electricity produced for each of these capacities of wind turbines. And if I press the clipboard, it's now calculating the critical excess for each of these wind capacities. And when it's finished, I can put in here, you can see that none of the wind power was lost for the first 1,000 megawatts. Then a small bit started to get lost at 2,000 megawatts, and that increased as I put in more and more wind power. And according to these results, I would say somewhere between 3,000 and 4,000 megawatts was the best time to stop installing more and more wind power. So this is the critical excess electricity production of our reference system. Now I want to start adding some heat pumps to my district heating system and see if that improves the operation. So large scale heat pumps. And I'll measure the same thing again, costs and how much wind power I'm losing, because I'm going to hope that my heat pumps will capture some of that surplus wind power and use it for heating purposes rather than just losing it. And let's put a total here, minimum. So I'm just using this to show my minimum price, 3139, which occurred at 4,000 megawatts. So let's go back then to the input tab sheet of EnergyPLAN, district heating, and under the heat pumps, I'm going to install some large-scale heat pumps. Another rule of thumb is that the heat pump capacity as a starting point is usually around 10 to 20% of the CHP capacity. That's just a place to start. It's not always the best capacity, but at least it is a starting point. So I'm going to start at 10%. I'll check what I put in the agenda. Maybe I had a different amount. Okay, I said 200 megawatts in the agenda, so let's stick with that, 20%. 200 megawatts of heat pumps, and that is going to be paid for based on the cost assumption here in the cost tab. So it's going to cost 3.4 million euro for every megawatt of heat pumps that I install. So you can see the 200 megawatts is now installed. I go back to my input sheet. You can see that this 200 megawatts of heat pumps has a coefficient of performance or an efficiency of 300%, or 3. So for every megawatt of electrical heat pump capacity, I get 3 megawatts of thermal capacity. So this 200 megawatts of heat pumps can produce 600 megawatts of heat. Now I'm going to run my calculations again. So I'll go to the output sheet, and hopefully now there'll be less critical excess because I've installed these heat pumps on the district heating system. So when there's some wind power that's not being used, the heat pumps will capture it and use it on the district heating systems. So I go to my Excel sheet, critical excess. You can see now that I don't have any critical excess for the first 2,000 megawatts of wind, and then it starts at 3,000 megawatts, but it's a bit less than it was when I didn't have the heat pumps. So for each one it's reduced. So we're now better at integrating wind with the large-scale heat pumps than we were when we didn't have the large-scale heat pumps. But I want to see if this makes economic sense. So let's go back to the output sheet and change the output to costs. And if I press the clipboard again, and it's finished, and now I'll paste the results. We can see that the heat pumps have made the system slightly cheaper. Very little, but at least it's a cost reduction of some sort. So it's only less than 0.5%, I would say, or even smaller. But at least we've managed to integrate more wind power and reduce the cost of the system slightly. So this means that the 200 megawatts of heat pumps that I installed are a socio-economically good idea, and they can allow more wind power to be integrated onto the system. So that's a demonstration of, let's check the agenda. I think that's all of the points covered. And of course you can change a lot of the assumptions that I made when I did this very simple case study of had a very simple relationship between electricity and heat demands and between the installed capacities of different units. So you can change those around to suit whatever specific study you're carrying out or whatever particular reference model you want to make. But you generally follow the same procedure. Of course, I'll just emphasize also that in this tutorial I only measured costs and critical excess electricity production. There's many other outputs that you could say represent what is the best system much better than those two metrics. For example, the total amount of fuel consumed, the CO2 emissions, how much renewable energy you have, and so on. And you can look into those different options depending on what needs you have yourself. But it's just to emphasize that what's defined as the best energy system might not necessarily be the cheapest energy system. I just happen to measure those things for this case study. Okay, so now we will move on to individual heat pumps and do another simple case study for analyzing individual heat pumps. For those of you who used EnergyPLAN in the past, there is a major new change in how we estimate the cost of individual heating units. So it's not so relevant for anybody who's brand new to EnergyPLAN, but for those of you who have used EnergyPLAN in the past, it's a very new feature. So I just want to explain that for people who have been using EnergyPLAN before. So if I go to the input sheet and then the individual tab, this is a list of all the individual heating demands that we have on the system. At the top we have the distribution of the individual heat demand and the distribution of individual solar production. And then down in the rest of the sheet we have a list of all the fuels and heat demands that are required by individual boilers on the system. And for my reference scenario, I've just put in 20 terawatt hours of oil and 20 terawatt hours of gas as the consumption in my imaginary reference model. So let's just put in 20 oil and 20 gas. In the old days, EnergyPLAN would use this heat demand that's calculated based on the efficiency of the boilers, of the oil boiler and the gas boiler. So you can see the 20 terawatt hours of oil is used at an efficiency of 85% on average to give a heat demand of 17 terawatt hours in the buildings. In the old days, that 17 terawatt hours was matched with this hourly distribution to find out what was the peak heat demand in individual buildings over the year. And then using that peak demand, the cost of those boilers was estimated. So under the cost sheet, down here where we put in individual heating unit costs to be per megawatt of heat as the unit of measurement for the costs of the individual heating units. And that was related to the peak heat demand over the year, which was estimated based on this distribution and this total annual heat demand. But we noticed when we did our calculations over the last few years that typically underestimated the price of the boilers, because the peak heat demand did not represent the peak installed capacity of boilers. So we've changed the methodology in EnergyPLAN so that instead of using the peak heat demand, it now estimates the total number of boilers installed, and then we put in a cost for each boiler. And the way that it estimates the total number of boilers installed is that you input what the total heat demand is, and you also input down here what is the average heat demand per building. So dividing the average heat demand per building by the total heat demand gives you the total number of buildings in your system. So if I go to the cost window, then you can see that EnergyPLAN is estimating that in my imaginary reference scenario, there's 2.3 million boilers in the system based on my average heat demand and my total heat demand. So 2,333,000 boilers. Then this price here represents how much does it cost for each boiler. And multiplying one by the other, you find out then how much the total costs are for the boilers in your system. And this methodology makes it very simple to do different alternatives for the individual heating components in EnergyPLAN, which I'll show you now in a second with the heat pumps. So if I go back to my input tab sheet, right now I have 20 terawatt hours of oil and 20 terawatt hours of gas, and that's 17 terawatt hours of heat demand for oil and 18 terawatt hours of heat demand by natural gas boilers. So my total heat demand is 35 terawatt hours. I'm going to run the results again with total costs for these new demands installed. So over here I'll call this individual heating, and this is my new reference scenario, and it has 20 terawatt hours of oil and gas, and I'm going to measure the costs in the first one. And you can see, because I'm now consuming all of this natural gas and oil, my costs have gone up a lot in this scenario versus what they were in my last step. So all of this extra fuel for the individual boilers is costing me around 3 billion euro per year extra. Let's just measure the critical excess, since we measured it for all the others, but it should not have changed because these boilers won't interact with the rest of the system. But let's just measure it anyway. So critical excess. And yeah, as you can see, it hasn't changed, which is what I would expect. And now let's change the oil boilers to heat pumps. So instead of having 20 terawatt hours of oil, we'll have 20 terawatt hours of heat pumps and gas. And we'll measure the same things, cost and critical excess. So if I go back to my EnergyPLAN model and I go to my input sheet, I'm going to remove the oil boilers. Instead of having 17 terawatt hours of heat demand from the oil boilers, I'm going to make that 0, and I'm going to put that 17 terawatt hours as heat pumps. So now my total heat demand is still 35 terawatt hours, but now it's coming from gas and heat pumps rather than gas and oil boilers. So in reality, in my imaginary world, I've removed all the oil boilers from the houses and I've put in heat pumps instead. And you can see that that has created an extra electricity demand to power all these heat pumps of about 5.7 terawatt hours per year. If I go to the cost window, it's now estimating that I have around 1.2 million boilers and about 1.1 million heat pumps. So you can see that's done in the same way that I mentioned earlier. Let's go to the output file. First thing we'll measure is critical excess. So we should have less critical excess now because we have these heat pumps to use some of the surplus wind power. It's finished. Critical excess. Yeah, and here we go. You can see that the critical excess is down even further now that we have the individual heat pumps. And now we go to the costs very quickly. You can see that replacing the oil boilers with the heat pumps has reduced the price of the energy system by about 300 million euro per year. So once again, we've been able to integrate more wind power and reduce the price of the energy system. So now the cheapest price with the individual ones is 6,372, whereas with the oil boilers it was 6,666. So we've added an extra 1,000 megawatts of wind power to the system and reduced the costs of the system. And this, at least in this particular world. So then that pretty much brings us to the end for today. Sorry, I'm a bit behind time, but I'll just end with giving you a sneak peek of the new energy plan, which we've been working on for the last while. So this is what is the new interface on EnergyPLAN, which will probably be called version 12 when it's released in January next year. So right now internally we're at EnergyPLAN version 11.7, but by the time we finished with all the new updates, it probably will have changed a lot more. And some of the nice new features that we've added is a new tree view system on the left-hand side of the model, so that if you don't like the tab sheets that we have, you can now use the tree view instead. And you can decide which one you want to use by turning them on and off in the new menu structure. And obviously the other new big feature that you can see right now is this new menu system that we have, which is to align ourselves with the ribbon structure that many of the Microsoft applications are using right now. We've also added some nice new buttons to this new menu system that make things a bit faster at exporting and copying some results. So that's some of the new features to look forward to when we release it in January next year. Thank you very much for your attention once again at the workshop. If anyone has any questions, please feel free to put them in the chat box and we'll try to answer any outstanding issues that you didn't understand. Otherwise, we'll call the tutorial to a close since we promised to finish at approximately 4 o'clock. So I'll just hang on for 30 seconds or a minute to see if anybody has any questions. Otherwise, thank you for attending and hopefully see you next time. So I just got two questions from Michael. In relation to the first one, I'll just go to the regulation tab sheet. This input on the bottom right is a way of changing the length of time over which a thermal storage is optimized. So if you, right now, you can imagine that people who own a thermal storage device cannot predict what the weather will be like in 6 months' time or 12 months' time or so on. So we have put in a default value of 2 weeks, saying that people who operate the thermal storage have an idea of what the weather is going to be like or the heat demands will be like over a 2-week period. But if you want to imagine an ideal situation where people understand what will happen over the full year, then you can change this number of days to be a full year of 366, which means that they can see what the heat demand will do over the full year and see what impact that has on your results. So like Michael suggested in the question, that's related to seasonal storage. In relation to the other one about increasing individual storage, if I wanted to increase the amount of storage in the individual buildings, I can do that over here under a column called heat storage under the individual tab. And what this means is that it's the number of days of heat storage that you have in each building. So if I put in, for example, under the heat pumps, that I have 1 day of average thermal storage in each building, it means that I have enough hot storage in each building to cover 1 day of the heat demands. So you can vary the individual storage by increasing the number of days of thermal storage that you have in each individual building. Right now, there's no automatic cost connected to that number. So if you put in that, if you vary that number, don't forget that under the cost additional tab, you might have to add something for example, increasing the storage, or let's say thermal storage in each building. And then you might have to add in a cost for that, depending on what your scenario is, or so on. There was a PP input warning. Yes, let me see. Can you recall which scenario it appeared? Oh, I think I know what might have happened. Maybe when I installed the heat pumps, I might have increased the electricity demand by 5.7 terawatt hours, which would have been added to the 20 terawatt hours, which would have given me a total of 25.6, and maybe I didn't have enough power plants to meet that new 25.6 terawatt hour electricity demand. So if that problem appears, you should either install more power plants or some other type of electricity producing units. So yes, it would need to be solved. For Michael has just put up another question about the district heating plants. If you have some district heating only systems, I would put them in group 1. But just one thing I will mention is that usually the amount of district heating that's provided by boiler-only systems is usually very, very small. And if it is very, very small, then you can perhaps just put it in to group 3 and you won't change your results dramatically. But ideally, it would be best to put the heat-only district heating systems in group 1. Just wait another minute or two so people can get some final questions. If you have a district heating system with only a boiler and a heat pump, then you have to put it in either group 2 or group 3 with the CHP capacity left at 0. Unfortunately, there's no heat pump option for the district heating group 1, and that's just because when it was programmed it wasn't added. In reality, you could say add heat pumps to these systems. So unfortunately, it's just not in the model yet, unless you have no inputs in group 2, for example, where you can just leave CHP 0 and put in heat pumps and boilers on their own. The just two last things, and I think we'll leave it then. Michael also has the problem of having heat pump on a district heating system with no CHP plant, and in that case, if you then I would advise you to just put the CHP as 0 and have heat pumps and boilers modeled on their own in group 2. If you do have something in group 2, then we can just put it on the wish list for the future to add heat pumps to group 1, and hopefully we can do it sometime in the new year after the new release. Then Susanna, in terms of the difference, there's no difference between the heat pumps in group 2 and group 3. The only difference between group 2 and group 3 is the way that the CHP plants have to function. So you can imagine that the CHP plants in group 2 are a bit more difficult to dispatch because they're linked to the heating demand also. So that means that the heat pumps might not get as much space in group 2 as they get in group 3, because in group 3 the CHP plants don't produce heat every time they produce electricity. And I think we'll wrap it up for today there, and if anyone has any further questions, feel free to put them on the EnergyPLAN forum on the website. So under energyplan.eu you have the forum, and we try to answer within 1 week if possible. So if you have any other questions, please send them to us and we'll try to answer them. Otherwise, we hope to see you at the next workshop, which will probably be in January or February next year after the new version is released. So thank you all for attending, and see you next time.